We're going to go over positive transcriptional control in repressible operons and inducible operons. Alright, so remember with positive transcriptional control, the regulatory protein we're going to be using is the activator protein. So that's what we're going to be using to turn the operon on and off. And remember that the definition for a repressible operon is it's always going to be turned on unless there's too much end product. So if I ask you on the test to define what a repressible operon is, that's the definition that I'm looking for. Okay, and then part B of the question that I might ask on the test would be if this repressible operon is under positive transcription control, how is it turned on? Okay, so if we're using positive transcriptional control, we need to think about where the activator protein would be if it's turned on. So the activator protein is going to bind to the activator binding site on the DNA, and that actually helps the RNA polymerase bind to the promoter. So when the activator protein is bound to the activator binding site, that helps the RNA polymerase bind to the promoter, and then it can go ahead and do transcription, transcribe the genes in the operon, and then those can be made into the proteins and the operon will be turned on. Okay, and then part C of the question would ask, how would this operon be turned off? So how we want to turn it off would be if there's too much end product around. Okay, so maybe we made too much of whatever the end product is. So we need to figure out how to get the activator protein off of the activator binding site. So how that happens is if we've got too much of our end product around, then the end product will bind to the activator protein, and that'll cause the activator protein to change shape, and that'll make it fall off the activator binding site. And now that the activator protein is no longer bound to the activator binding site, RNA polymerase is no longer able to bind to the promoter, so there won't be any transcription, and that's going to turn the operon off, okay, which is what you want because you don't want to keep making the end product because you've got too much. And then our last scenario is using positive transcriptional control to turn an inducible operon on and off. So again, we're going to be using an activator protein. That'll be our regulatory protein to turn this operon on and off. But now we're going to be working with our inducible operon. And if I ask you to define that on the test, an inducible operon is going to be turned off unless the substrate's present. Okay, so if I put this scenario on the test, the next thing I would ask after asking you to define what an inducible operon is I would ask you, how would this inducible operon be turned off if it's under positive transcriptional control? So we've got to think about where the activator protein would be if this operon is turned off. So if it's turned off, the activator protein would not be bound to the activator binding site. And then that means that the RNA polymerase cannot bind to the promoter because the activator protein is not around to help it. So there won't be any transcription. And that'll turn this inducible operon off. Okay, and then the next question I would ask would be, how would we turn this inducible operon on? And we're going to turn this on if our substrate is present. So how would we get the activator protein to bind to the activator binding site? Is that if our substrate is present, it will bind to the activator protein, and that'll change the activator protein's shape and allow it to bind to the activator binding site. And now that the activator protein is bound to the activator binding site, RNA polymerase can bind to the promoter. And now it can go ahead and transcribe the DNA. And now we've turned on our operon. So that's how we would turn it on. Okay, so that would be our last scenario that I could put on the test. Okay, and then another operon just to know would be the tryptophan or TrpOperon. And this operon is a repressible operon that's under negative transcriptional control. It contains 5 structural genes. A structural gene is just a gene that codes for a protein. And these genes will code for enzymes that are used to make the amino acid tryptophan. So let's just look at this operon. So if we're using negative transcriptional control to turn this operon on and off, the regulatory protein we're going to be using would be a repressor protein. And then just the definition of a repressible operon. Remember that these are always going to be turned on unless there's too much end product. And the end product in this case would be tryptophan. Okay, so if we want to draw this repressible operon, this TrpOperon turned on, we've got to think about where a repressor protein would be. And the repressor protein would need to be off of the operator for this TrpOperon to be turned on. And if a repressor protein is off of the operator, that means that our RNA polymerase can bind to the promoter. And we can go ahead and do transcription. So that would be the TrpOperon turned on. Okay, but if we've ended up making too much end product, we made too much tryptophan, we need to turn this TrpOperon off. So we need to change the shape of our repressor protein to get it to bind to the operator. So how this is going to happen is that our end product, tryptophan, will bind to the repressor protein, and that'll change the shape of the repressor protein and allow it to bind to the operator. And now the repressor protein is in the way, so RNA polymerase can't bind to the promoter. And there's going to be no transcription. And so that'll turn our operon off, which is good because we don't want to make any more tryptophan because we've got too much of it.